Okay, so today we will start discussion on quantum Fourier transform and its applications. Quantum Fourier transform is actually one of the most important fundamental algorithms in quantum computing. So far, we studied algorithms that required oracles. For example, we studied Dice-Jozsa, Bernstein-Vazirani, and Simon's algorithm that help understand the difference between a quantum computer and a classical computer, and they all required oracles. Like we need to have an access to a black box that we can access in superposition. Similarly, when we studied the quantum search algorithm proposed by Grover, we saw that it also requires an oracle. But quantum Fourier transform is another class of algorithms, is part of another class of algorithm that doesn't require an oracle. Everything is specified inside the algorithm. So this is a sort of an algorithm that will completely run on a quantum computer without having to build any oracle. And number two, this is also an algorithm that actually provides an exponential speed up over a classical, over corresponding classical algorithms, but also have a lot of applications as well. So other algorithms that you might have heard, for example, Shor's factoring algorithm that provides an exponentially faster way of finding factors of composite numbers, that also relies on quantum Fourier transform as well. So the discussion that we will begin today is going to be an extremely important part. So we won't be, of course, able to study a lot of advanced algorithm, but many of the advanced algorithm, they also rely on quantum Fourier transform. And actually, there's another algorithm that we will discuss tomorrow. It's called quantum phase estimation. So a combination of quantum Fourier transform and quantum phase estimation, they are used in a lot of algorithms for many applications, including factoring. And this is all, these two algorithms, quantum Fourier transform and quantum phase estimation, they're also integral part of Hamiltonian simulation algorithms, where we simulate a quantum mechanical system. For example, if you want to compute the energies of a molecule or another quantum mechanical system. And they also have applications to area that is not directly to Hamiltonian simulation. For example, solving a set of linear equations or some optimization problems, for example, variational algorithms, etc. All of these rely on quantum Fourier transform and quantum phase estimation. So the purpose of saying all of this is that what we are going to study from today is an integral and important part of quantum algorithms. Okay, so what we will do today is we will discuss what quantum Fourier transform is, its definition for quantum, computing, and then we will discuss its circuit and then implement in the cascade. And hopefully this will provide you an understanding of at least how to perform a quantum Fourier transform. Along the way, I will also be discussing, some of the benefits of quantum Fourier, of Fourier transform in general, which are actually available in quantum Fourier transform. So we wouldn't be, requiring any knowledge of classical Fourier transform that you might have encountered in other, courses, especially in mathematics and maybe in some engineering disciplines. But the general idea, the general use of Fourier transform in classical applications is finding the period or frequencies or spectrum of a given function. So that is what essentially is the benefit in quantum Fourier transform as well, that we are able to find periods of functions. And a lot of applications, depend on finding periods of the functions and also the eigenvalues of some operators. So we will be discussing all of these things in the 3 lectures that we have for this course. So let me start by sharing my screen. I can make it big. Okay, so I will start with the definition of quantum Fourier transform, and then we will, sort of develop a visualization that what does quantum Fourier transform do, and then we will see why particular definition of QFT has been chosen, and then we will discuss the algorithm, a circuit for quantum Fourier transform, and we will implement it in Qiskit. And the one related thing is quantum inverse quantum Fourier transform. Actually, that is also used a lot. So with QFT, we will also discuss inverse QFT circuit as well. Okay, so let me just start by giving the definition, and a little bit later I will motivate why this particular definition is chosen. So suppose you have a quantum state J, and we want to find its quantum Fourier transform. It's defined as 1 over n square root, and suppose there are n bits, so capital N is 2 power n. By the way, I sometimes talk about bits, so from context it should be clear that when it actually means qubits and when it means classical bits. If you're talking about a binary representation in a classical computer, then these are classical bits, and if you're talking about n qubits, then this really is n qubits that I'm talking about. Sum over k from 0 to n minus 1 exponential 2 pi iota j into k over n and k. So this is the definition that we will be using for this quantum Fourier transform. And let me just explain different terms in this definition to help you understand. So this quantity J is a decimal label for the actual bit state, the qubit state like this: n minus 1, n minus 2, n minus 3, all the way to J1, J0. And this is nothing but a shorthand notation for this. Which basically means that if I have n qubits, n physical qubits, so each of this label represents a state of the corresponding qubit. And as we have already discussed that this is just a way of writing, and then this label J is computed from this binary representation like this. So J is, let me start with an example. Suppose you have a J state like 1, 0, 1. So this means that J is, so this 1 is at the unit place. So 1 plus this 0 is at the next place, 2 power 1 into 0 plus So this 1 is at the next place, so 2 power 2 into 1. So this is 4 plus 1, 5. So in general, if you have a number like this, then j is given by this, the 2 power n minus 1, jn minus 1 plus 2 power n minus 2, jn minus 2. So there's a multiplication here plus and so on. So 2 power 1 into j1 plus 2 power 0 into j0. So by the way, there's a different notation for this lecture that I'm using here than either in the book by Nelson and Chuang or the Qiskit online textbook that is available. So you will not be able to find a one-to-one correspondence between the notes that we are preparing right now in this lecture and what is available in Nelson and Chuang book or the Qiskit online textbook. And the reason is this, that I find this notation in line with what we have been doing before, because this is the notation that we have settled on already, where this is our least significant qubit and this is the most significant qubit on the left side. And also when we draw circuit, we have developed this convention that our J0 would be on the top when we are drawing the circuit, and then J1, J2 all the way to Jn minus 1. And it's important to stick with one convention, because sometimes you might have drawn a circuit on paper, but if you transfer it to a computer program, if you don't follow the same notation, you might end up reversing the order of qubits, which will mess up your algorithm. So I'm trying to stick with the notation that we have already agreed upon. Okay, so this is the label J. So is everybody okay with this label? Or how to compute it? For example, if I have a state J as 1 0 1 0, this corresponds to the label decimal label J as so this is n is equal to 4. So I start from n is equal to 3, 8 into 1 plus 4 into 0 plus 2 into 1 plus 0. So this is 10. So this is a state that I can in decimal notation write as 10. So this is not 1 0, this is actually 10. So similarly, if I have a state J as 1 1 1, so this essentially means that J is 15. So I can write this as 15. So this is how I compute this decimal value J. Okay, and similarly, this K, so this J that is appearing here as a label is appearing here as the numerical quantity. So in the algorithm today, before this, whenever we were working with these decimal label, this was just a convenience that we were computing this sometime this label J, so that instead of writing the whole binary state, for example, instead of writing this 1 1 1 1, we could just write 15. So this was just a convenience. But right now, this decimal value is also used in this algorithm itself. Similarly, this number K and this state K is defined like this. So K is just like J, a shorthand for Kn minus 1, Kn minus 2, Kn minus 3, all the way to K1, K0. And K is again 2 power n minus 1 into Kn minus 1. And by the way, these numbers can be only 0 or 1. So these are binary numbers, plus 2 power n minus 2 into Kn minus 2, all the way to K1 into 2 plus K0. So this is how we can compute the decimal value of K. And you just have to keep in mind that we start at 2 power 0, and the most significant bit is multiplied with 2 power n minus 1, not with 2 power n, where capital N is 2 power n. So and in the sum, in the definition, you see we go all the way from k0 to n minus 1, because with n bits, the highest decimal that we can get is n minus 1 when all the digits are 1 1 1 1. So that's why this sum goes from 0 to n minus 1. Okay, let me elaborate this example little bit further by taking a few examples to show how this definition works. Because actually, the circuit for quantum Fourier transform is really easy to get if you just understand this definition very well. So that's why I'm spending some time in understanding the definition itself. So let's say we have only one qubit. That small n is 1, which means that capital N is 2. So my definition QFTJ is now 1 over square root. K goes from 0 to 1 because it was n minus 1, exponential 2 pi iota j k over 2 k. And since in this case j can be 0 1, k can be 0 1, so everything is very simple. So let's try to find what is the Fourier transform of state 0. So when j is 0, what we get is this. So j is 0, so a 0 here, so exponential power 0 is 1, so this factor is gone. And in my sum, I first have to put k0 plus, then k is 1. So this is what I get. And this is nothing but the plus state, if you remember. So quantum Fourier transform of state 0 is plus. So similarly, let's say what is the Fourier transform of 1, which we can get 1 over 2 square root k going from 0 to 1 exponential 2 pi iota. So now this j is 1. So 1 into k is k. So I have k by 2 k. So let's perform the sum. When k is 0, when this is 0, so exponential 0 is 1. So no phase term come with 0 plus. When k is 1, so this is 2 cancels with 2, and I'm left with exponential pi iota. And exponential pi iota is cosine pi plus iota sine pi, which is, so cosine pi is minus 1, sine pi is 0, so exponential pi iota is just minus 1, which means that I get a minus sign here. So when k is 1, this term gives me a minus sign. So this is nothing but the minus state, as we used to call it. So QFT of one state is this. Perfect. So in a single qubit system, what is happening is this, that if this is, let's say, block sphere, and my state 0 is being Fourier transformed in such a way that it becomes plus state. Similarly, if I have an input state 1, this is being Fourier transformed to the minus state. And we know what circuit can do this, a Hadamard transform. So for single qubit, the QFT circuit is just this thing. So J naught, a Hadamard into, so this goes to, so let's develop some notation like this, that this, QFTJ, let's call it some J tilde. So which means that J naught goes to J naught tilde, which is the QFT of J naught using a Hadamard transform. So a single Hadamard is actually a Fourier transform operator, a single qubit Fourier transform operator, which transform straight from computational basis to this Fourier basis of plus minus. So any question so far or confusion? Perfect. So let's continue with the examples. And let me now take a 2-bit example. So suppose small n is 2, which means capital N is 4. And let's try to find out the Fourier transform of this 0, 0 state. So this would be 1 over 4 square root. Some k goes from 0 to 3 exponential 2 pi iota jk over 4 k. But j is 0 because this is 0, 0. So this factor will go away and we will only have 1 over 2 square root. So let's just, write it 1 over. Okay, so let me write it like this. So this is 1 over 2 square root square, because when I take this 2 and square root cancel away and I will get half, which is what this 1 over 4 square root is. So this term goes away. So k is first 0, which means that this is 0, 0. Then k is 1, which is 0, 1. Then k is 2. Then k is 3. And this, by the way, I can easily write like this. Right? Because if I take this product, this is exactly what we will get. 0 into 0, 0, 1, 1, 0, 1, 1. And this is nothing but plus state. So a 0, 0 goes to plus plus. So this is the Fourier transform of the 0, 0 state. Let's now take one more, example. And let me take Fourier transform of 0, 1. This is a little bit non-trivial. And then we will generalize. So Fourier transform of 0, 1 is 1 over 4 square root again. K goes from 0 to 3 exponential 2 pi iota. Now in place of j, I have a decimal value of 1. So 1 into k over 4. So this becomes 1 over 2 square root, and let me write it like this. K 0 to 3. So this is 1 into k is k. So 4 and 2 goes away. So I'm left with exponential iota pi k over 2, because this 2 and 4 cancel, I'm left with. So let's now open this sum. So for k 0, so exponential 0 is plus 1. So this is 0, 0 as it is. For k 1, so this k 1 is 0, 1 state. And when this is 1, this becomes exponential iota pi by 2. And exponential iota pi by 2 is nothing but cos pi by 2 plus iota sine pi by 2. So this is 1, so I'm left with iota. So for the next term, we have iota 0, 1. Now, the term after this, for 1, 0, this k is 2. When k is 2, this 2 cancel with 2, and we have exponential iota pi, so I get minus 1, 0. And for the last term, k is 3. So when k is 3, so this is 3 by 2. So exponential iota pi 3 by 2 is cos 3 pi by 2 plus iota sine 3 pi by 2. So this is 0 and this is -1. So I'm left with minus iota. So this is minus iota 1 1 state. So this is what we get to. So with a couple of hit and trials, you can separate them also into two states like this. So this is 0 minus 1 into 1 over square root 2 0 plus iota 1, and you can see. So 0 into 0 is 0 0, 0 into 1 iota, so this is plus iota 0 1. So then 1 into 0 is with minus sign, so this is minus, and 1 into 1 is 1 1, and this is iota, and this minus sign is here. And this is nothing but this state is minus, and this state is what we call plus iota state. But essentially, this is a state with a phase exponential iota pi by 2, because this iota can be. So this is a phase. This is a state with the phase pi, and this is a state with phase phi term as pi by 2. Anyway, so let's plot them on block sphere. This previous state, this one, how did 0 0 transform, and how did 0 1 transform? And you can compute the rest yourself if you like. So let's just see how does 0 0 state transform. So 0 0 in computational basis state is like this. So 0 0. So these were qubits before Fourier transform, and once QFT is done, so first of all, we see that Fourier transform is not entangling the qubits, because after the Fourier transform, we were still able to write them as a product state. So this is a plus state. So this is a plus state. So this is plus, and this is plus. So after Fourier transform, both states are in this vertical plane, and they're both along plus plus state. Let's see how this 0 1 state transformed. So 0 1 transformed to minus plus iota state. So if we have starting state 0, sorry, and 1. So after Fourier transform, they become, on left side I have minus state, and on right side I have plus iota state. So minus state is this, and plus iota state is along y-axis, if you remember. And even if you forget, you can see right from here. So this is a state with phase phi, because this minus is nothing but iota pi, and this plus iota is nothing but exponential pi by 2. So this has a phase pi, and this has a phase pi by 2 on block sphere. So this has a phase, this is the x-axis, so this is a phase of pi, and this is x-axis, so this is a phase pi by 2. So this is a plus state. But one thing is common still between this transform state and this transform state. All the qubits are in this vertical plane. They are not lifted up or down on the block sphere. So what this Fourier transform is doing is transforming the states, these basis states 0 1 to these new basis states, which are states in this xy plane in the block sphere. So we are going from computational basis state to something which we call a Fourier basis state. So essentially, a Fourier transform is a change of basis, because we can check that the new states which are forming, we can still write functions in terms of these new states. Similarly, if you transform, this 1 0 state and find its QFT, we will see that these are also states somewhere on this plane and so on. And similarly, if I transform 1, 1, they will also lie in this state. And let's actually see in general what will happen. So let's now begin generalizing this transformation and start from, again, n is equal to 2 state. So let's say we have a 2-qubit state J, and we want to find its Fourier transform. 2-qubit state mean I have 1 qubit J1 and I have another qubit J0. So this Fourier transform can be written as 1 over square root 4 k going from 0 to 3 exponential 2 pi iota j k over 4. Now we want to develop this sort of state of qubits in a product state at the end to visualize them. So it's easier that instead of expanding this sum in terms of k, we expand this sum in terms of k naught and k1 separately, and we'll see in a minute what happens. So this 1 over 4 square root can be written as 1 over 2 square root, and this sum I can write it like this: sum over k1 from 0 to 1, sum over k0 from 0 to 1. And so this becomes exponential 2 pi iota, and this j, let's keep this j here, but this k, let me write it in an expanded form. This k is 2k1 plus k naught over 4, and this k is k1 k naught. So it means I can now separate these two sums over two different terms. There's a sum over k1, there's a sum over k naught. So the sum over k1 can be separated out. I have to take the terms in k1 over here. So exponential 2 pi iota j 2k1 over 4. So this is j k1 over 2, because this 2 will cancel with 4 and I have 2. So this k1 can be separated, because this is nothing but a tensor product of k1 and k naught state. So tensor sum over k naught from 0 to 1 exponential 2 pi iota j k naught over 4 k naught. So this is how I'm able to separate out this sum over k1 and k naught separately. So let's take this 1 over square root 2 from this side over there for normalization purpose, and expand this sum as well. So when I expand this sum, this will become 1 over square root 2, and first k1 is 0. So when k1 is 0, this k1 is 0, exponential 0 is 1, so I have 0 plus when k1 is 1, I have exponential 2 pi iota j over 2. So exponential, so let's cancel this 2 as well. So I have iota pi. So this k1 is 1, so this is gone. So I have left with j pi j 1. Tensor 1 over square root 2. So I'm keeping 1 here and bringing 1 over there. So again, when k naught is 0, so this is 0, this phase term goes away, 0 plus. So when k naught is 1, exponential, so I have, let's cancel this 2 with this 2. So we have exponential iota pi by 2 j 1. So this is the circuit, but we can sort of simplify it a little bit, because this j is nothing but 2j1 plus j0. So let's put this j back in there, and we will be left with 1 over 2 square root 0 plus exponential iota 2 pi j1, because when this j is replaced with 2j1, so this is 2 pi j1 into, and since there's a plus, I can break this exponential like this, iota pi j naught 1. So this is 1 qubit. The second qubit, this one is 1 over square root 2, 0 plus exponential. So when I put 2j1, so this 2 cancels away. So I have iota pi j1. And then when I put this j naught, so this j naught remains. So I have exponential iota pi by 2 j naught 1. So let's see what happens here. So this term is 1. Doesn't matter what value of j1 is, because when j1 is 0, so this exponential 0 is 1. But even when this j1 is 1, exponential iota 2 pi is exponential iota 2 pi is cos 2 pi plus iota sine 2 pi, and this cos 2 pi is 1, this sine 2 pi is 0. So this is always 1. So this term is always 1. Which means I can eliminate it. So I have finally 1 over square root 2, 0 plus exponential iota pi j naught 1, answer 1 over square root 2, 0 exponential iota pi j1 exponential iota pi by 2 j naught 2. So this is QFT of J1, J0. Okay, so let's now try to make a circuit for it. So I have to transform one qubit into this and another qubit into this state. So let's see how I can do it. Now, before we even go to do that, let's think about what gives, circuit gives a phase pi. So this term means that when J naught, so let's concentrate on this one. When J naught is 0, you should get 0 plus 1. And when J naught is 1, you should get 0, because when this is 1, exponential iota pi is minus 1, minus 1. So there's a factor 1 over square root 2. And what gate can do this? This can be done by a Hadamard on J naught, right? Because a Hadamard on J naught will give us exactly this state. When J naught is in 0 state, you get plus state. When J naught is in 1 state, you get the minus state. So it means this qubit can easily be obtained, and that is by doing a Hadamard on J naught. So if I want to draw a circuit, and let's say this is my J naught qubit, which is in the top of the circuit, all I have to do is do a Hadamard on this one. And this will give me this first qubit. And what we are calling this is my qubit, because we have introduced notation that this is equal to J1. So this is J1 tilde, J naught tilde. So this is the J1 tilde qubit. So this will give us J1 tilde. So let's see how to get this one. So this is a little bit tough, because there are two things that are happening with this qubit. There's a phase over here and there's a phase over here. This phase depends on J1 and this phase depends on J naught. So this phase is which is J1 dependent, and this is a phase of pi. I can easily get it. All I have to do is place a Hadamard on J1. But this phase is a phase which is pi by 2, but this upon on J naught. So it means I need a phase gate which is controlled by J naught. Okay, so let's do it like this. Let me actually redraw this part of the circuit. So let's take this header mod a little bit ahead because I need to do a control operation because of J naught. So J1, I first apply a header mod always, because this header mod is actually a controlled phase gate with respect to J1 anyway. When J1 is 0, there's no phase. When J1 is 1, it is, since we get a minus sign, which is equivalent to exponential iota pi. So this header mod works for exponential iota pi J1. And then I need a phase gate, a phase pi by 2, but not always, only when this J naught is 1. So I need a control with respect to this. So this will give me the J naught qubit after transformation. So this is the circuit for 2-qubit Fourier transform. This has only one trouble, and that is that we have set this convention that our least significant qubit should come on top and most significant qubit on the bottom. But what we are getting over here is that my J1 is coming on top and J naught is coming on the bottom. So what I can do, that I can apply a swap gate here. So this will take this qubit on top, which is my J naught, and this qubit will come here, which is J1. So with this swap operation, now I have a perfectly arranged qubits. So this is a circuit for 2-bit quantum Fourier transform. Any question about this? So do all of you get this point of adding phases? Like this is just a header mod controlled by J1. So to control a header mod by J1, all I can do actually easily that just put a header mod right on J1. And then this was a phase which was to be controlled by J naught. But now I had no choice but to introduce a controlled phase gate. In Qiskit, you can easily implement it with the command CP. So this controlled phase gate with a phase of pi by 2 controlled by J naught can give me this term. And with these two things, I can get my qubit in this state. So if you understand this, you essentially understand quantum Fourier transform. Is everybody okay? All right. So before I discuss the general quantum Fourier transform circuit, let me introduce this idea, why this particular choice of definition of quantum Fourier transform. So what's the motivation for definition? So for that, let's see this thing. So suppose I have a quantum state phi, which is a superposition state like this. Okay, and let's say we transform this state under our definition that we have just proposed. So if I take a Q of t of this state phi, we get this. And this QFT is a quantum Fourier operator. So this will go right to this, state through the sum, because it's a linear operator and operates on these quantum states. Now this we can replace using the definition that we have proposed. So this is 1 over n square root sum over k from 0 to n minus 1 exponential 2 pi iota jkn sum over k. Okay, so let me now take this sum over k outside and everything else inside. So this sum over j xj exponential, and there's 1 over n square root 2 pi iota jk over n. Okay. So this is nothing but if we think about this larger sum, this is coefficients, kth coefficient of the state k. So let's call this yk, and I can write my state k goes from 0 to n minus 1 as yk, like this. So a QFT of state phi gives us another state whose coefficients yk are related to the coefficients of older state phi xj through this relation. So yk are given by 1 over n square root sum over j from 0 to n minus 1 xj exponential 2 pi iota jk over. And this is nothing but a classical Fourier transform. More precisely, it's a discrete Fourier transform, because this xj are discrete coefficients. So this particular definition that we have chosen essentially relates the coefficients of any quantum state. When we apply the quantum Fourier transform to the superposition state, its coefficients are essentially transformed according to the classical discrete Fourier transform. So if you have a state, let's say like this, some 0, 1, and so on, and they have some coefficients subject to the normalization condition, and if you apply a QFT on them, the coefficients of the new state will be related to the coefficients of the older state through the classical discrete Fourier transform. So this definition for the Fourier transform that we have used here is actually motivated from this fact that it has a direct correspondence with the classical discrete Fourier transform. So it means all the properties and applications of Fourier transform in the classical domain, they are directly applicable in the quantum domain as well, if we apply the Fourier operator that we just proposed. So any questions so far? Okay, so now we will extend this 2-qubit algorithm to a general n-qubit algorithm. So for that, let me start discussing the general algorithm. For QFT. And let's now start from the definition again, which is And I hope if you understood the 2-qubit circuit, you will not face much trouble with this one. But I'll still try to go slowly from it so that nothing is confusing. Okay, so I can write a transformed circuit as this, J tilde, and just to, show what is our qubit labeling, it's this. So this J tilde from here is 1 over 2 power n square root k 0 to n minus 1 exponential 2 pi iota, and this J is again the decimal representation of state J, and similarly K comes from this state K. And as we did for the 2-qubit circuit, let's divide this sum over K into sum over individual qubits. So a sum over Kn minus 1 from 0 to 1, Kn minus 2, 0 to 1, all the way to sum over K1, sum over K0. And we will have to break this K into its component Kn1, etc. So 2 power n minus 1, Kn minus 1, 2 power n minus 2, Kn minus 2, all the way to 2K1 plus K0. And this state K is Kn minus 1, Kn minus 2, all the way to tensor K1, tensor K0. So it means that I can write it like this, that let's take 1 over 2 square root for each of this qubit. So for the first one, for this sum over K0, let's start from the left. So for the first sum over Kn minus 1, I will have sum over Kn minus 1 from 0 to 1. And so there all of these terms are adding in the power. So I can write it into a product form, that so each product term will have each of this binary term Kn minus 1, Kn minus 2, etc. So the term that goes with this one would be exponential 2 pi iota J, and there's this n as well, capital N. So this capital N is 2 power n, which means that actually let me make it a little bit simpler before I start this bifurcation into individual terms. So let's just keep this sum right now. So Kn minus 1, there's a sum over Kn minus 2, there's a sum over K1, sum over K0. So let's take this 2 inside this sum. So this term will become 2 power n, and then there is this n here. So this becomes exponential iota pi j. So this 2n cancel with this 2n, so I have Kn minus 1. So this is n minus 2. So there's a 2 coming from here. So this is 2n minus 1, and then there's 2n here. So this becomes Kn minus 2 over 2. So then the next term would be Kn minus 3 over 4. And then the second last term K1. So there's a 2 here, there's a 2 here, 4, 2 power 2, and there is a capital N here. So this becomes K1 over 2 power n minus 2. And then there's this k naught, which is 2 power n minus 1. And then I have this qubits state kn minus 1, kn minus 2, all the way to k1, k naught. Okay, now we can separate this all these qubits into separate terms. So the first term on the leftmost depends on this qubit. So this is sum over kn minus 1 from 0 to 1 exponential iota pi j kn minus 1 j kn minus 1 kn minus 1 tensor 1 over 2 square root sum over kn minus 2 from 0 to 1 exponential iota pi j kn minus 2 over 2 kn minus 1 tensor all the way to, let's write these terms here. So for the second last term, it is sum over k1 from 0 to 1 exponential iota pi j. So this is k1 over 2 power n minus 2, k1 over 2 power n minus 2, k1 tensor 1 over square root 2 sum over k naught exponential iota pi j k naught 2 power n minus 1 k naught. So these are the states of the k qubit. So let's see, let's now run this sum on this qubit. So this is when kn minus 1 is 0. So this exponential into 0 is 1. So I am left with 0 plus. So when kn minus 1 is 1, so the next term is exponential iota pi j 1, and this square root over 2 tensor. So in the next term, it is the first term is 0 because when kn minus 2 is 0, so exponential 0 is 1. So 0 plus exponential iota pi j. When this kn minus 2 is 1, so this is half. So let's put this pi by 2 into 1 square. So this second last term would then be 0 plus exponential iota pi over 2 power n minus 2 j 1. And then the last term is 0 plus exponential iota pi over 2 power n minus 1 into j 1. So this is the state of the qubits. And just to remind you, on the left side, we have this thing that we have this Fourier transform of state j, which was jn minus 1, jn minus 2, all the way to j1, j0. So this is our qubit state jn minus 1. So let's just see what this is. Can we simplify it? So jn minus 1 is 1 over under root 2, 0 plus. Now this, let me write the expression for j. This is exponential iota pi, and j is nothing but 2 power n minus 1, jn minus 1 plus 2 power n minus 2, jn minus 2, all the way to j1 plus j naught into 1. Now, if we look at these exponentials, we can see one thing. First of all, I can write it into different terms. So this is uh, exponential iota. Let me first of all also take 2 common out of here. So if I take 2 common, this becomes 2 pi, and then this becomes 2 power n minus 2. So this is 2 power n minus 2 into jn minus 1. The next term is exponential 2 pi 2 power n minus 3 jn minus 2 all the way to exponential iota 2 pi j1 and exponential iota pi j0 1. Now we can see one thing very easily, that this number is 1, because this is exponential iota 2 pi j1. So even if j1 is 0, it is 1. If j1 is 1, even then it's 1. Similarly, the term next to it is 1, because they're all multiple of 2 pi. So this number is an integer. It's multiple of 2 pi. Exponential multiple of 2 pi is always 1. So this is 1. So all the phase terms are 1 except this last term, because exponential iota pi j naught is 1 when j naught is 0, and it is minus 1 when j naught is 1. So this term simplifies to exponential 0 plus exponential iota pi j naught, which I can easily get with a Hadamard gate. So the most significant qubit can easily be obtained by applying a Hadamard on j naught, because a Hadamard on j naught will give me this required phase. So this bit is taken care of. Let's see the next term. So the next term is exponential iota pi by 2j. Is everybody okay with this term? Okay, so let's go to the next term, which is 1 over 2 square root 0 plus exponential iota pi by 2j. Let's expand j again. So 2 power n minus 1, jn minus 1, 2 power n minus 2, jn minus 2, all the way to 2j1 plus j naught. Now in this case, we see that this is j naught pi over 2, so non-integer. It's not a multiple of 2 pi, so this term remains. This is 2j1 over iota pi by 2, so 2 cancels with 2, so this is still a multiple of pi, so this term remains. But the term just before this was 4j2, which means that this 4 divided by 2 is 2, so this term still yield a product of 2 pi, so this term is 1. So all of these terms, their exponential will go to 1, and we will only be left with 0 plus exponential iota pi j1 exponential iota pi by 2 j0 1. So it means now I have a Hadamard on j1, but I have to apply a phase gate with a phase pi by 2 controlled by j naught to get this term jn minus 2. So Hadamard on j1 and a pi by 2 phase with respect to j naught, controlled by j naught. Okay, so this way we can continue and see that the next term is actually a Hadamard on j2, a pi by 2 phase controlled by j1, and a pi by 4 phase controlled by j0, and so on. And we keep going. And let's see what's actually this second last term. So this term is exponential iota pi over 2 power n minus 2j. So this term was j1, 1 over square root 2, 0 plus exponential iota pi over 2 power n minus 1 j1. Let's just check to make sure that's right. 2 power n minus 2 j. Oh, sorry, 2 power n minus 2. So this is this. So let's expand this j. So this j is j 2 power n minus 1 j n minus 1 2 power n minus 2 j n minus 2 all the way to 2j1 plus j naught into 1. So in this case, let's see if this is integer or not. So when I divide 2 power n minus 1 with 2 power n minus 2, I still get 2. So I will get 2. So this term will go away because this is a product of 2 pi. But this term is still pi because this 2 power n minus 2 cancels with 2 power n minus 2 and I'm left with pi. So and all the terms after this are going to be there. So this is 0 exponential iota. So this is pi jn minus 2. The next term exponential iota pi by 2 jn minus 3 all the way to exponential iota pi by. So this is 2. So 2 divided by 2 power n minus 2 is 2. This is plus, so n minus 3 j1. So the last term is exponential iota pi j0 2 power n minus 2 into 1. So now we have a Hadamard with respect to jn minus 2, but then all of these are controlled phase gates. So this is a phase gate pi by 2 controlled by jn minus 3. The next is phase gate with phase pi by 4 and so on. So this is a gate pi over 2n minus 3 phase controlled by j1, and the last gate is pi over 2n minus 2 controlled by j0. So, and the last qubit is 1 over 0 plus exponential iota pi over 2n minus 1 into j1, which means that all of these terms remain, and we have exponential iota. So this is the expansion, only division is 2n minus 1. So the first term is pi jn minus 1. The next term is exponential iota pi by 2 jn minus 2 iota pi by 4 jn minus 3, and all the way to exponential iota pi over 2n minus 2 j1 exponential iota pi 2n minus 1 j naught 1. So we have a Hadamard on jn minus 1. So this is j naught Hadamard on jn minus 1, and then there are all these controlled phase gates. Let me now draw the circuit. And while drawing the circle, let's start from the simplest one. Actually, let's start from the most complicated one. So let's try to get this j naught. So for that, I first need a Hadamard on jn minus 1. So first of all, let's say I have my qubit j naught, j1, all the way to jn minus 2, jn minus 1. So these are the starting qubits. So this j naught tilde can be obtained by first applying a Hadamard to jn minus 1. So let me apply a Hadamard. Then a controlled phase gate of phase pi by 2 controlled by jn minus 2. So let's say a phase gate pi by 2 controlled by this. The next is a phase gate of pi by 4 controlled by this. And this is the way we continue all the way. And at the end, I will have this gate, let's say phase pi over 2n minus 2 controlled by J1, and then a phase gate pi over 2n minus 1 controlled by J0. So this will give me this one, J0 tilde. Okay, the one just before it, this one, J1 tilde, has a header mod on Jn2, and then control gates with respect to n minus 3 and all the way up. So it means once I'm done with this one, so we start with this one, a header mod, then a control phase pi by 2, controlled by just the qubit and above this, and then we keep going. And then similarly, we keep going up, and at the end, we have the simplest case that I can get this is J0. This is J0. Where is Jn minus 1? Okay, this one. So this is the simplest one. All I need is a header mod on J0. So this is J0, and a header mod will give me Jn minus 1 tilde. So we are able to get all of these, outputs, but there's only one trouble, and that is that they're coming in the reverse order. This J0 should have been on the top, and Jn minus 1 should have been at the bottom. So what we can do easily, that we can apply the swap gates like this, that the highest and the lowest most are swapped with each other, and then this one is, these two are swapped, and so on. So this will reverse the order, that J0 goes on top and Jn minus 1 goes to the bottom. So this is the way that we can now, put them back in the order such that our least significant come on the top and our most significant come at the bottom. So any question regarding the circuit? Perfect. So let's now compute its performance. That how many gates we actually need to perform this Fourier transform. So if we have, n bits, we see that for this bit, we have n gates. So there's this header mod gate on Jn minus 1, and then there's this gate which is controlled by n minus 2, and all the way coming to this loss control gate, we have a total of n gates. So to make up this J0 tilde bit, we need n gates. And then for the qubit just above it, we need one less gate, because we have a header mod, and then the control gates are only with respect to the remaining qubit. So this, and then we can go on, and for the topmost qubit, I have only one qubit, gate, and for J1 we have 2 gates, and so on. And you can easily, find a sum of this series, which is n into n plus 2, I think, over 6, which is, of the order of n square. Where, this is n square plus 2n, but when n is large, this term is proportional to n square. So this is the leading term. So we see that we need the total number of gates which are proportional to n square. We also need actually the swap gates, and they are n by 2. So the swap gates, to swap these qubits, they're n by, if there are n bits, we need n by 2 swap gates to swap these. So there are n by 2 gates per swapping, but still, this n square term is the leading term, because this is just n, this is proportional to n. So we need gates which are proportional to n square to implement this quantum Fourier transform. And classically, the best possible gates, the algorithms still require orders, number of operations that are proportional to 2 power n, and actually even faster, because I think it's n 2 power n. So not just exponential, but also multiply with n. So this n square number of operations, they are far less than n 2 power n when n is large. So that's why the quantum Fourier transform is an exponentially faster way of computing a Fourier transform on a quantum computer than a classical computer. And that's why if we can somehow engineer a classical algorithm and use, if it involves a Fourier transform, and we can replace the Fourier transform part with the quantum Fourier transform part, there's a possibility. There's a possibility, because I'll just say later that what does that mean, that we can make the algorithm exponentially faster. And actually that's what Shor also did. He knew that classically to factor 2 numbers, we need to perform a classical Fourier transform. And he was able to replace that classical Fourier transform part with the quantum Fourier transform, and the algorithm in one go became an exponentially faster algorithm than the classical algorithm. The trick is that you replace quantum Fourier transform in such a way that the quantum advantage is not lost because of measurement. You see, the reason is this, that I can compute the quantum Fourier transform in n square operation, but my final answer is going to be in a superposition form over here. And to really find the Fourier transform of a function from the input, I will need many more operations than n square, because I will have to run the circuit many times to adequately measure the Fourier transform. So if your purpose is just to find the Fourier transform, then actually there is almost no quantum advantage, because you will lose the advantage that you gain in number of operations in running the circuit again and again. But if you can find a way that you can feed this quantum Fourier transform into an algorithm that can use the Fourier transform in superposition form, that you don't have to measure the Fourier transform over here, and it can take you to the final answer in one go, then you can get the quantum advantage. And that's actually mostly the use of quantum Fourier transform in quantum algorithms, that it's used as a part of a subroutine, that there is some bigger algorithm, and maybe on part of it we are performing some Fourier transform, and there's some other things that are going on. And in that case, we are able to get an advantage over classical computation if we can judicially use a quantum Fourier transform. Any questions? Okay, if not, let me, before I go to Qiskit, I want to describe one other quick related concept, and that is inverse operation. Suppose you have a quantum circuit. It has some, unitary operation A, B, C, D, etc., which means that there are a bunch of, qubits. You first perform operation D on them, and then you perform a unitary operation C, then a unitary operation B, then and a unitary operation A. So this is what you're doing. If your input is psi, your output psi prime is this. That at this stage you have D into psi. At this stage you have D into psi into C, and so on. At the output, you have this state. So whatever you perform here, it comes, over here and so on. Now suppose you want to get psi back from psi prime. So what we need to do? Can you guess?
We would have to run it through the gates again in the same order.
No. We can easily do it if we just think about this. So let's multiply with A inverse on both sides. This will give me B, C, D psi. Let's now apply B inverse on both sides, then C inverse, and then D inverse, and then ultimately psi is going to be D inverse, C inverse, B inverse, A inverse, psi. So not only you have to apply operations A, B, C, D in reverse, but you have to also take their inverses. And fortunately, since all of these are unitary operations, A inverse is nothing but A dagger. And always remember, A dagger has two parts. It is, so A dagger is two parts, it's a transpose and a conjugate. So it means that if I want to get psi back from psi prime, we need to run a circuit like this. I first apply A dagger, then I apply B dagger, then I apply C dagger, then I apply D dagger, and then I get my output. So we need to apply these operations in reverse, that you should start from A, then B, then C, then D, but also their daggers. And daggers, have these transpose and conjugate part. And by the way, if your matrix is only like, for example, if you have a phase gate. So a phase gate is exponential iota theta like this. So that's why, we can write it 0, 0, 0 plus exponential iota theta 1, 1. Because when this phase gate is applicable to, let's say, some alpha 0, beta 1, it doesn't disturb this 0 state, but it gives a phase exponential iota theta to this 1 state. And if this is, 1 by 2 already, that then this is 1 and this is here. And its P dagger would be what? Its P dagger would be 1, 0, 0 exponential minus iota theta. Because when we take a transpose, because of the 0, the transpose gives the same matrix. But when I take dagger, I get exponential minus iota theta. So it means a phase gate has its inverse as a phase gate with a minus of this phase. And if there's a Hadamard, we already know that Hadamard is its own inverse. So the inverse of Hadamard is just Hadamard itself. And I think you can check easily as well, because Hadamard is 1 over 2 square root 1, 1, 1 minus 1, like this, right? So when I take its transpose, it's still the same. Okay, so I'm discussing this because I need to come up with a way of finding the inverse quantum Fourier transform, because a lot of time we need it in our algorithms. So to do inverse quantum Fourier transform, I have to invert two operations, because my Fourier transform had these two parts. So there's one part, which is this algorithm, and the other part is this inversion. So my inverse quantum Fourier transform should first these swap operations, and then after that it should run this circuit in opposite. But not only in opposite, all these phases have to come with minus sign during the inverse Fourier transform operation, because the inverse of the phase gate is a phase gate with the minus of the phase. Okay. Good. So let me stop sharing this and discuss the implementation on Qiskit.